Okay, next up on physics is topic B, which is entitled Generating Energy. There's just a couple of terms I want to make sure that you're happy with. Those are current and voltage. So current is the rate at which the electricity is flowing. More specifically, it's the rate at which the charge carriers are flowing, which is most often electrons. But you just need to understand that it's to do with how fast the electricity is transferred from one place to another. And the voltage is a measure of how much energy the electricity is able to transfer. And again, more specifically, it would be how much energy each electron is able to transfer. Now, both of them are going to affect how much energy we transfer in total, because if I've got low energy electrons but they're going really quickly, they could transfer as much energy as high energy electrons that are going slowly. So if I want to know about how much energy we're transferring with electricity, I need to know about both the current and the voltage. But in essence, the current is how fast is it going, and the voltage is how much energy does it have. So there are two basic ways to generate electricity. It's pretty straightforward, really. You take a magnet and you take a coil of wire, so literally just wire that you round into a circle, round and round and round. So I can imagine maybe winding it around a pencil. Typically we do it around something bigger, but you get the idea of the shape. So you've got your magnet and you've got your coil of wire, and you can either move your magnet inside your coil of wire, so you could push it in and out of the coil, or put it in the coil and then twist it around. Or you can twist the coil of wire around the magnet. Doesn't matter as long as one of them is moving compared to the other. And in both cases, what this does is the magnet forces the electrons inside the wire to move, which causes a current. Now, from this method of generating electricity, the current that we produce is alternating current, so AC. So it doesn't just go in one direction. So if you think about the idea of where we had the magnet going in and out of the coil, when the magnet's going in, it'll make the electrons move in one direction, and when it comes back out again, it'll make them go in the opposite direction. So it goes backwards and forwards. So that's why it's alternating current. Don't worry about getting your head around how it's alternating when we're rotating things. Just trust me, it is. You don't need to know the fine detail on this one. So we know that we can make the electricity by moving either the magnet or the coil. And if we want to increase the current that we produce, there are a few things we can do. We can use a stronger magnet, we can have more turns of wire, or we can move the coil or the magnet, whichever we're moving, move them faster. Okay, so these principles are how we make electricity in the big power stations. So over at Drax or Eggborough, you can pick them, we're kind of surrounded where we are. They all use the same principle, but there are a few steps to how they get to this movement. So in a power station, if it is a fuel burning power station, so for instance coal, oil or gas, or biomass, if we're burning the biomass, so biomass is just sort of waste organic matter. We burn the fuel to make heat. We use that heat to boil water. The steam from the water rises and turns turbines, and the turbine then either turns the coil or the magnet inside our generator, which then makes our electricity. Now, when we're talking about power stations, we're kind of talking about magnets the size of double-decker buses, so much, much bigger scale. Now, this basic principle is the same whatever source of energy you're using. So with so we had the fuel burning ones, so coal, oil, gas and some types of biomass. Nuclear power stations work in a similar way, but they just use nuclear energy to create the heat, which then boils water, which turns to steam, which turns to turbine, which turns to generator. And there are some types of biomass that are basically fermented and they produce a gas, most often methane. And we can just use that gas either as a fuel or, depending on how we've created it, we can use the gas directly to turn the turbine. But it's the same basic principle. Typically, boil water using your energy, water makes steam, steam turns to turbine, turbine turns to generator. Okay, so a little bit more on alternating current. As I said earlier, alternating current just means that the current goes in one direction and then in the other. And as long as the current is flowing energy is transferred. It doesn't matter that the electrons go backwards and forwards, they can still transfer their energy. Now, this is the type of current that's produced by dynamos and generators. Dynamos, I hope you've come across before. Typically, I don't think they get used for this very much anymore, but they used to be on bikes, so as you pedalled, your light came on, but when you stop pedaling, your light goes off. So those are dynamos. And dynamos and generators produce AC current, whereas batteries produce direct currents. They produce current that just goes in one direction. So they might ask you about how they're different. And if we want to know more about the alternating currents, we use a fancy looking device with loads of buttons on the front called an oscilloscope. Now, it's a really crazy looking machine, but all it does is it draws a graph of voltage against time. Or I can choose to make it draw a graph of current against time, it doesn't matter. Whichever I did, they would look very similar to the one I've drawn down here. So if you look, we've got, it sort of looks like a sine wave, so that just means when we get this nice shape where it goes up, through the middle, down and back again. And it'll just be this repeating over and over again. What I've given you here is just one cycle, so one time period. So here to here is one full oscillation, so the current's gone forwards, then it's gone backwards, and it's back to where it started. And that would be one cycle. And we could measure the time period for that. So if you were asked for the time period, all you will need to do is pick a point from where it starts, where it goes through one whole cycle, and just measure the time on the x-axis. And you can either go from peak to peak or trough to trough. It's just you want one full wavelength. So this is very similar to the stuff when we were looking at waves. It's just that instead of having it travelling through space, we're showing it travelling through time. So you can just measure the time period straight off the axis. And if we're talking about what's going on with the generator, so if you remember I said that when we put the magnet into the coil, the electrons, the current flows in one direction. So that would be this section here. Then when I remove the magnet, it flows in the opposite direction, so this would be this section here. So in order to make the bit that you can see here, I would have to have put a magnet into the coil and then pulled it back out again. Or I would have had to have rotated it all the way through 360 degrees. So the first section would be a half turn, the next section would be another half turn. But you just need to get the idea that we have to have movement to make these things, and half the movement gets you half of it, and you have to go back in the opposite direction to get the other half. So efficiency is the last bit. Oh, just spotted a typo. Efficiency is the measure of, oh god, that's horribly written, I apologise greatly. Efficiency is a measure of how much of the energy that is supplied is used for something useful. Please write that down, not what I've typed. Basically, we just want to know how much of what we put in got used for what we wanted it to be used for. And the equation for this, which will be given to you in the exam, is efficiency equals the useful energy output divided by the total energy input. Now that will always give you a number less than 1, because nothing is completely efficient. Now if you're asked to calculate the percentage efficiency, you take the efficiency and you multiply it by 100, and that will give you a number less than 100. So if something's not completely efficient, it means that the energy must be going somewhere else, must be getting wasted. Now in power stations, a lot of energy is wasted. Now we use the energy from the fuel to heat water, which becomes steam, which turns the turbine. Unfortunately, we can't just heat the water. It'd be great if we could, but when we burn our fuel, it's going to heat the air, it's going to heat the container I've got the water in, it's going to heat the container that I've got my fuel in, it's going to heat everything around it. So what we're trying to say is that the energy gets lost to the surroundings. So in power stations, it's that heat energy that we lose. It doesn't all go into our water. So we don't turn it all to steam as efficiently as we could, so we don't get it all turned to electricity, because we're just heating everything. We can't be selective. So you need to know that for power stations. You need to know how the energy is wasted. And that is it for this one. There is nothing that's different on the higher and the foundation. You all need to know all of it. So don't forget, if you've got any questions, do not hesitate to ask me. Okay?